Tonight I want to take you somewhere quiet, somewhere far from the rush of daily life, into a question that might seem simple at first but holds within it one of the most fascinating mysteries of our universe. We're going to explore something that touches every moment of your existence, something that carries the warmth of stars to your skin and brings the colours of sunset to your eyes. We're talking about light itself, and more specifically, about a secret that physics has been quietly keeping for over a century. You see, despite what you might have learned in school, despite what seems like common knowledge, no one has ever actually measured the speed of light the way you might think they have. It's a statement that might sound impossible, even wrong at first, something you could easily dismiss as a mistake or misunderstanding. But the more we look at it together, the more quietly intriguing it becomes. What if I told you that every measurement of light speed, every number you've ever seen written in textbooks, carries within it a hidden assumption that we cannot escape? What if the very nature of light and time are so deeply intertwined that separating them to measure one independently of the other is not just difficult, but fundamentally impossible? Before we drift deeper into this cosmic puzzle, I'm curious about where you're joining me from tonight. Are you nestled in bed somewhere in a bustling city, or perhaps in a quiet countryside where the stars shine clearer? What time is it where you are? Is it late evening with the last rays of sunlight fading from your window, or deep in the night when the world around you has gone silent? Wherever you are, whenever you're listening, you're part of this journey we're taking together through one of physics' most beautiful mysteries. And if you find yourself drawn into this gentle exploration of light and time, if these cosmic wanderings help carry you toward peaceful sleep, perhaps you'd like to join me for more of these nighttime journeys into the universe's quiet secrets. A gentle like or subscribe would mean we could explore more of these mysteries together, drifting through questions about black holes, quantum realms, and the fabric of space-time itself on other quiet nights like this one. Now, let's begin with something familiar, something you've experienced countless times today without even thinking about it: light. It surrounds us so completely that we rarely pause to wonder what it actually is. Right now, as you rest there, light is streaming all around you, even in darkness. Radio waves from distant stations, infrared radiation from every warm object in your room, perhaps the soft glow of a phone screen or the moonlight filtering through your window. All of it is light, just in different forms, different wavelengths, different energies. And all of it, we're told, travels at exactly the same speed through empty space. That famous number you might remember from school, 299,792,458 meters per second. It's a number so precise, so exact, that it seems like someone must have measured it with incredible accuracy. And in a way, they have. Scientists have indeed performed countless experiments, bounced light off mirrors, timed its journey across laboratories and even to the moon and back. But here's where our mystery begins to whisper its first hints. Every single one of these measurements, without exception, has measured the round-trip speed of light, never its one-way journey. Think about that for a moment. Let it settle into your mind like a stone dropping into still water. When we measure the speed of light, we always send it somewhere and wait for it to come back. We time how long the complete journey takes, then divide by the distance travelled. It seems so simple, so straightforward, but hidden in this measurement is an assumption so fundamental that most of us never even realise we're making it. We assume that light travels at the same speed in both directions. We assume that the journey there takes exactly as long as the journey back. And why wouldn't we? It seems perfectly reasonable, almost obvious. But the universe, as we're learning more and more each day, doesn't always care about what seems reasonable to us. You see, to measure the one-way speed of light, to actually clock how fast light travels from point A to point B without returning, we would need synchronized clocks at both locations. One clock to mark when the light leaves, another to mark when it arrives. Simple enough, you might think. But here's where the universe plays its subtle trick, where the mystery deepens into something profound. How do you synchronize two clocks that are separated by distance? The most accurate way would be to send a signal between them, and the fastest possible signal is, of course, light itself. But to use light to synchronize clocks, we would need to know how fast that light signal travels. And to know how fast light travels one way, we need synchronized clocks. We're caught in a perfect circle, a logical loop that has no beginning and no end. This isn't just a practical problem, something we might solve with better technology or cleverer experiments. It goes deeper than that. all the way down to the fundamental nature of time itself. You see, Einstein discovered something remarkable over a century ago, something that changed everything we thought we knew about the universe. He found that time and space are not separate things, fixed and absolute, but are woven together into a single fabric we call space-time. And in this fabric, the speed of light isn't just another speed like the speed of sound or the speed of a train. It's the speed at which causality itself propagates through the universe. It's the maximum rate at which any information, any influence, any change can spread from one point to another. It's not just about light, it's about the fundamental structure of reality itself. When Einstein developed his special theory of relativity, he made a choice, a convention that has shaped physics ever since. He assumed that light travels at the same speed in all directions. This assumption, called the isotropy of light speed, allows us to synchronize clocks in a consistent way, to build a coherent picture of how events unfold in space-time. But here's the beautiful, mysterious truth. This assumption is just that, an assumption. It's not something we can prove. It's not something we can measure. It's a choice we make about how to describe the universe, and remarkably, we could make a different choice and physics would still work perfectly fine. Imagine for a moment that light doesn't travel at the same speed in all directions. Perhaps it travels at infinite speed in one direction and at half the conventionally measured speed in the opposite direction. This might sound absurd, impossible even. But mathematically, physically, observationally, such a universe would be indistinguishable from one where light travels at the same speed in all directions. Every experiment we could perform, every observation we could make, would give us exactly the same results. The round-trip speed would still be that famous constant. Time dilation, length contraction, all the strange and wonderful effects of relativity would still occur exactly as we observe them. The universe would look and behave identically, even though the underlying reality would be profoundly different. This is not just idle speculation or philosophical musing. Serious physicists have examined this question carefully, and they've found that the one-way speed of light is not just unknown, it's unknowable. It's what philosophers of science call a convention, a choice we make about how to coordinate our descriptions of nature. We choose to say that light travels at the same speed in all directions because it's simple, elegant, and symmetric. But the universe is under no obligation to respect our aesthetic preferences. Let me paint you a picture of what this means in practical terms. Imagine you're standing in a vast, dark field on a clear night. The stars shine above you, ancient light that has traveled for years, centuries, millennia to reach your eyes. When you look at the North Star, you're seeing light that left that star over 400 years ago. Or are you? If light travels at different speeds in different directions, that light might have left the star yesterday or 1,000,000 years ago, depending on which direction it traveled to reach you. The entire cosmic timeline, our understanding of when things happened in the universe, depends on our assumption about how light travels through space. This might feel unsettling at first, like the ground beneath our understanding of physics has suddenly become less solid, but I invite you to see it differently, to find in this uncertainty not confusion but wonder. The universe has given us a freedom here, a choice in how we describe its workings, and in that freedom there's something beautiful, something that speaks to the relationship between human consciousness and physical reality. We are not just passive observers of nature, we are active participants in creating the framework through which we understand it. As you lie there tonight, perhaps feeling your breathing slow, your thoughts beginning to drift like clouds across an evening sky, consider what this means for our everyday experience of light and time. Every photograph ever taken captures light that has made a journey to the camera's sensor. But how long did that journey really take? Every star you've ever seen, every sunset you've ever watched, every rainbow that has ever formed in the spray of a garden hose, all of these involve light traveling through space and time in ways that are fundamentally mysterious to us. The history of measuring light's speed is itself a fascinating journey through human ingenuity and cosmic mystery. For most of human history, light was thought to travel instantaneously. When you opened your eyes, it seemed obvious that you immediately saw everything around you. There was no sense of delay, no perception of light taking time to travel. Even great thinkers like Kepler and Descartes believed that light's speed was infinite. But in 1676, a Danish astronomer named Ole Rømer noticed something peculiar while studying the moons of Jupiter. He was timing their eclipses, watching as they passed behind the giant planet and emerged again. And he noticed that the timing varied depending on where Earth was in its orbit. When Earth was closer to Jupiter, the eclipses happened slightly earlier than predicted. When Earth was farther away, they happened slightly later. Römer realized what was happening. The light from Jupiter's moons was taking time to reach Earth, and that time changed as the distance changed. From these observations, he made the first quantitative estimate of light speed, calculating that it would take light about 22 minutes to cross the diameter of Earth's orbit. This wasn't quite right. We now know it takes about 16 minutes, but it was remarkably close for such an early measurement, and more importantly, it established that light had a finite speed, that it took time to travel through space. Over the following centuries, scientists developed increasingly clever ways to measure light speed. In 1849, Hippolyte Fizeau used a rapidly rotating toothed wheel to chop a beam of light into pulses. He sent these pulses to a mirror several kilometers away and measured how fast the wheel had to spin for the returning pulses to pass through the gaps between the teeth. It was like creating a precise optical clockwork, using mechanical motion to measure something far faster than any mechanical system. A year later, Léon Foucault improved on this method using a rotating mirror instead of a toothed wheel. His apparatus could fit in a single room, bouncing light back and forth between mirrors to create a longer path in a smaller space. These experiments were marvels of precision engineering, requiring incredibly stable equipment and careful measurement. But notice something important about all of these methods. In every case, the light was sent out and returned. The mirror at the far end, whether kilometers away or just across the room, always sent the light back to its starting point. The round trip was always measured, never the one-way journey. Albert Michelson, who would later become the first American to win a Nobel Prize in physics, spent decades refining these measurements. He created increasingly sophisticated instruments, eventually measuring light speed to an accuracy of just a few kilometers per second. His work with Edward Morley in 1887 was intended to detect the Earth's motion through the luminiferous ether, the substance that scientists then believed filled all of space and carried light waves. Instead, their experiment found something far more profound. No matter how fast or in what direction Earth was moving, light always seemed to travel at the same speed relative to their laboratory. This null result, as it came to be known, was one of the great mysteries that led Einstein to his special theory of relativity. If light always travels at the same speed relative to every observer, regardless of their motion, then something fundamental about our understanding of space and time had to change. Einstein realized that the solution was to abandon the idea of absolute simultaneity, the notion that there is a universal now that exists across all of space. Instead, simultaneity becomes relative, dependent on the observer's frame of reference. And this relativity of simultaneity is intimately connected to our inability to measure the one-way speed of light. Think about what happens when we try to synchronize two clocks separated by distance. We might start them at the same time and then move them apart, but the very act of moving them introduces complications due to time dilation. Or we might send a light signal from one to the other, but then we need to know how fast that signal travels. We could try using slow transport, moving a clock very slowly from one location to another to minimize time dilation effects. But even infinitely slow transport doesn't solve the problem completely. The synchronization of distant clocks and the one-way speed of light are two sides of the same coin, each defining the other in an endless dance of circular logic. This brings us to something even more profound about the nature of physical reality. The laws of physics, as we understand them, are expressed in terms of mathematical relationships between measurable quantities, but not everything that appears in our equations corresponds to something we can independently measure. Some quantities are like the one-way speed of light, defined by convention rather than determined by experiment. This doesn't make physics arbitrary or subjective, but it does reveal something deep about the relationship between mathematical description and physical reality. In our everyday lives, we never notice this ambiguity because all of our experiences involve round trips of light or signals. When you look in a mirror, light travels from your face to the mirror and back to your eyes. When you have a phone conversation with someone on the other side of the world, electromagnetic signals travel back and forth through cables and satellites. Even when astronomers observe distant galaxies, they're detecting light that has completed a kind of round trip through time, traveling from the galaxy to us and then, through our observations and theories, connecting back to our understanding of that galaxy's past. As you rest there in the quiet of night, perhaps you can feel how this mystery connects to the deeper rhythms of existence. Time itself, that river we all float upon, might not flow the way we imagine. In one direction, moments might cascade rapidly, light racing at infinite speed, causes instantly becoming effects. In the opposite direction, time might crawl, light creeping along at half its conventional speed, effects lagging far behind their causes. Yet from within this stream, floating along with it, we would notice no difference. Our clocks would tick at their familiar rate, our thoughts would flow at their usual pace, and the universe would appear exactly as it does now. Modern experiments have pushed our measurements of light speed to extraordinary precision. Using laser interferometry, scientists can detect changes in distance smaller than the width of a proton. Atomic clocks can measure time intervals to better than 1 part in a quintillion. Yet with all this precision, we still measure only round-trip speeds. We bounce laser light off retroreflectors placed on the moon by Apollo astronauts, timing the round trip to measure the distance to the moon with centimeter accuracy. We synchronize GPS satellites using signals that travel up and back down, never one way alone. Every measurement, no matter how sophisticated, carries within it that same fundamental assumption about light's isotropy. Some physicists have explored what would happen if we abandoned this assumption. What if light really does travel at different speeds in different directions? The mathematics works out beautifully, though it requires us to think about space and time in unfamiliar ways. In such a universe, the concept of simultaneity would be even more relative than Einstein imagined. Events that appear simultaneous from one perspective might be separated by vast stretches of time from another. The entire cosmic history, the story of how galaxies formed and stars were born, would need to be retold in a new temporal framework. Yet remarkably, all observable phenomena would remain unchanged. The cosmic microwave background radiation would still show the same tiny fluctuations that seeded the formation of galaxies. Supernovas would still explode with the same brightness, their light curves revealing the expansion of the universe. Gravitational waves would still ripple through space-time at the speed of light, or rather, at the speed of causality, which is what we really mean when we talk about light speed in the context of relativity. This is perhaps the most profound aspect of the whole mystery. The speed of light isn't really about light at all. It's about the maximum speed of causality, the fastest rate at which any cause can produce an effect across space. Light happens to travel at this speed because photons have no mass, nothing to slow them down below the universal speed limit. But gravitational waves also travel at this speed, as do any other massless particles or disturbances in the fabric of space-time itself. When we talk about measuring the speed of light, we're really talking about measuring the fundamental rate at which the universe updates itself, the cosmic refresh rate of reality. You might wonder why this matters, why physicists and philosophers spend time thinking about something that seems to have no practical consequences. If we can never measure the one-way speed of light, if different assumptions lead to identical observations, why not just accept the conventional view and move on? The answer touches on something essential about the nature of science and our quest to understand reality. Science isn't just about making predictions or building useful technologies, it's about understanding what we can know and what we cannot, about mapping the boundaries between measurable reality and theoretical convention. This question also connects to deeper issues in the philosophy of science. What does it mean for something to be real if it cannot, even in principle, be measured? Are we discovering the true nature of reality, or are we inventing useful descriptions that help us navigate our experiences? These are questions that have occupied thinkers for centuries, and the one-way speed of light provides a concrete example of how these philosophical issues manifest in actual physics. As the night deepens around you, as your breathing perhaps becomes slower and more regular, consider how this mystery reflects the broader nature of human knowledge. We live in a universe that reveals itself to us only partially, always keeping some of its secrets hidden behind veils of fundamental uncertainty. We cannot know the exact position and momentum of a particle simultaneously. We cannot see beyond the cosmic horizon where the expansion of space carries light away faster than it can travel toward us, and we cannot measure the one-way speed of light, that most basic property of the carrier of all information in the universe. Yet within these limitations, we have built an extraordinary understanding of nature. We can predict the motion of planets with stunning accuracy, design computers that perform billions of calculations per second, and peer back in time to see galaxies as they were billions of years ago. The boundaries of our knowledge are not walls that constrain us, but rather the shape of the space within which our understanding can grow and flourish. They define not what we cannot do, but rather the arena within which we can explore, discover, and wonder. The story of light speed measurements continues today in laboratories around the world. Scientists use optical cavities where light bounces back and forth millions of times, building up resonances that depend sensitively on light speed. They cool atoms to near absolute zero, creating Bose-Einstein condensates where light can be slowed to walking pace or even stopped entirely. They study the quantum nature of light, individual photons that exist in superpositions of different paths and arrival times until the moment of measurement collapses their wave functions. In all of these experiments, the round-trip nature of measurement remains inescapable. Even when scientists think they've found a way around it, careful analysis always reveals that somewhere, hidden in the experimental setup or the theoretical framework, the assumption of light's isotropy has crept back in. It's like trying to see your own eyes without a mirror, to step outside of space-time to observe it from beyond. The universe seems to have built this limitation into its very structure, a fundamental barrier between what can be known and what must be assumed. Yet there's something beautiful in this limitation, something that speaks to the harmony between human consciousness and cosmic law. We are beings embedded in space-time, made of atoms that obey quantum mechanics, held together by electromagnetic forces that propagate at the speed of light. We cannot step outside this framework to observe it objectively, because we are part of it, woven into its very fabric. Our inability to measure the one-way speed of light is not a failure of our instruments or our intelligence, but a reflection of our deep integration with the universe we seek to understand. Imagine for a moment that you could somehow measure the true one-way speed of light, that you could determine once and for all whether it really is the same in all directions. What would change? The equations of physics would need to be rewritten in a more complex form, but they would still predict all the same phenomena. Engineers would need to adjust their calculations, but all our technologies would continue to work exactly as they do now. The universe would look exactly the same, but our description of it would have lost some of its elegant simplicity. This is perhaps why most physicists are content with the conventional assumption that light travels at the same speed in all directions. It's not that they believe this is necessarily true in some absolute sense, but rather that it provides the simplest, most elegant framework for describing what we observe. In science, as in art, there is a beauty in simplicity, a preference for descriptions that capture the maximum amount of phenomenon with the minimum amount of assumption. The isotropy of light speed gives us clean, symmetric equations that treat all directions of space equally, reflecting the apparent symmetry of the universe itself. As you drift deeper into the quiet spaces of evening thought, consider how this connects to your own experience of light and time. Every moment of your life, every sight you've ever seen, has been mediated by light-making journeys whose true duration we cannot know. The sun you see, if you glimpsed it today, showed you its surface as it was about 8 minutes ago, or maybe it was 4 minutes, or 16, or any other combination that averages to 8 for the round trip. The moon, if it's shining through your window tonight, is showing you its face from about a second ago, or perhaps half a second, or 2 seconds, the uncertainty hidden in that one-way journey across the cosmic dark. Even the simplest experiences become mysterious when viewed through this lens. When you look across the room, how long does it take the light to travel from the wall to your eyes? The round trip would take only nanoseconds, far too brief to perceive. But the one-way journey? It could be instantaneous, the wall connecting to your eyes through light that travels infinitely fast in your direction. Or it could take longer, the photons creeping across the room while time itself adjusts to hide the asymmetry from your perception. There's no way to tell, no experiment that could reveal the truth, only the eternal mystery of light's one-way passage through space. This uncertainty extends beyond light to encompass our entire understanding of cosmic history. When astronomers observe distant galaxies, they calculate their age based on how long light has taken to reach us. But if light travels at different speeds in different directions, these ages become ambiguous. A galaxy that appears to be 10 billion years old might actually be much older or younger, depending on the direction from which its light approached us. The entire timeline of cosmic evolution, from the Big Bang to the present, rests on our conventional assumption about light's speed. Yet remarkably, the relationships between events remain unchanged. If Galaxy A formed before Galaxy B, this ordering is preserved regardless of our assumptions about light speed. The relative sequence of cosmic events, the causal connections between them, these remain fixed even as their absolute timing shifts like shadows on a wall. It's as if the universe has two kinds of time, the rigid time of causality that determines what can influence what, and the flexible time of convention that we use to label when things happen. Some physicists have suggested that this ambiguity might have practical consequences in extreme conditions. Near black holes, where space-time is dramatically warped, might the one-way speed of a light become measurably anisotropic? In the early universe, when space itself was rapidly inflating, could light have traveled at different speeds in different directions? These are speculative ideas, far from established science, but they hint at ways that this seemingly abstract question might connect to observable phenomena. There have been attempts to measure the one-way speed of light using cosmic observations. Some scientists have looked for variations in the behavior of distant supernovas depending on their direction in the sky. Others have studied the cosmic microwave background, searching for patterns that might reveal an underlying asymmetry in how light propagates. So far, all of these observations are consistent with light traveling at the same speed in all directions, but they're also consistent with certain types of anisotropy that would be undetectable by these methods. The quantum nature of light adds another layer to this mystery. In quantum mechanics, a photon doesn't have a definite path through space. Instead, it exists in a superposition of all possible paths, each contributing to the probability of where the photon might be detected. When we talk about the speed of light in quantum terms, we're really talking about the phase velocity of the electromagnetic wave function, a mathematical abstraction that only becomes physical at the moment of measurement. How does this quantum description relate to the one-way speed of light? It's a question that pushes at the boundaries of our understanding, where quantum mechanics meets relativity in ways we're still trying to fully comprehend. As you lie there in the darkness, perhaps feeling sleep beginning to approach like a slow tide, think about how this mystery connects to the broader tapestry of physical law. The universe seems to be built on symmetries, patterns that remain unchanged under various transformations. There's the symmetry of physical laws across time, which gives us conservation of energy. There's the symmetry across space, which gives us conservation of momentum. And there's the rotational symmetry that makes physics work the same way regardless of which direction we face. The assumed isotropy of light speed is another kind of symmetry, one that we impose on our descriptions rather than derive from observation. But the universe also loves to break symmetries in subtle ways. The weak nuclear force violates mirror symmetry, treating left and right differently at the subatomic level. The universe contains more matter than antimatter, breaking what should be a perfect symmetry between particles and antiparticles. Could the speed of light also hide a broken symmetry, a preferred direction in space that would reveal itself if only we could measure it? It's possible, though we may never know for certain. The philosophical implications of this uncertainty ripple outward into questions about the nature of scientific knowledge itself. If we cannot measure something even in principle, is it meaningful to say it has a true value? This touches on old debates between realists, who believe in an objective reality independent of observation, and empiricists, who argue that only measurable quantities have physical meaning. The one-way speed of light sits at the intersection of these viewpoints, challenging us to think carefully about what we mean by physical reality. Consider, too, how this relates to the role of convention in science. We choose to use meters and seconds to measure distance and time, but these are arbitrary human constructs. We choose to use base 10 for our number system, though the universe shows no preference for this choice. And we choose to assume light travels at the same speed in all directions, a convention that shapes how we synchronize clocks and coordinate events across space. These conventions are not discoveries about nature but decisions about how to describe what we observe. They're the human contribution to the partnership between mind and cosmos that we call physics. In your daily life, you navigate using GPS satellites that depend on precise timing of light signals. Your phone synchronizes its clock using protocols that assume light travels at the same speed in both directions. The entire technological infrastructure of modern civilization rests on this assumption, not because it's necessarily true, but because it works. because it gives us a consistent framework for coordinating our activities across the globe and beyond. The convention becomes reality through our collective agreement to use it. As the night continues its slow journey toward dawn, somewhere far from where you rest, scientists continue to push at the boundaries of what we can measure about light. They're developing new types of atomic clocks that can measure time to even more extraordinary precision. They're building gravitational wave detectors that can sense ripples in space-time smaller than the nucleus of an atom. They're planning missions to send spacecraft to the outer solar system and beyond, where the vast distances might reveal new aspects of how light and gravity behave. Yet through all of these advances, the one-way speed of light remains unmeasurable, a fundamental limitation that seems to be built into the structure of space-time itself. It's a humbling reminder that even as our knowledge expands, even as we peer deeper into the quantum realm and farther into the cosmic distance, there remain mysteries that lie not just beyond our current reach, but beyond any possible reach. These are not failures of science, but features of the universe, aspects of reality that teach us as much through their unknowability as others do through their measurement. The way we handle this limitation reveals something important about the scientific method. Rather than being paralyzed by what we cannot know, scientists have found ways to work within the constraint, to build theories that acknowledge the ambiguity, while still making precise predictions about what we can observe. This is the pragmatic beauty of physics, its ability to navigate around the unmeasurable, while still mapping the territory of the knowable with extraordinary accuracy. Think about how this principle extends to other areas of physics. In quantum mechanics, we cannot know a particle's exact position and momentum simultaneously, but we can calculate probability distributions that tell us where we're likely to find it. In general relativity, we cannot define a global notion of simultaneity in curved space-time, but we can still predict how objects will move and how time will dilate. In thermodynamics, we cannot track the individual motions of every molecule in a gas, but we can describe the gas's temperature and pressure with perfect accuracy. Each limitation becomes not a barrier, but a signpost, pointing us toward the right level of description for understanding nature. The speed of light connects all of these domains. It appears in the equations of quantum field theory, setting the scale for virtual particle interactions. It shows up in general relativity, determining how fast gravitational effects propagate. It's central to electromagnetism, defining the relationship between electric and magnetic fields. And through all of these appearances, it carries with it that fundamental ambiguity about its one-way speed, an uncertainty that propagates through all of physics like a whispered secret that everyone knows but no one can prove. As you rest there in the gentle embrace of approaching sleep, feeling perhaps the soft weight of blankets and the quiet rhythm of your own breathing, you're surrounded by light moving at speeds we cannot truly know. Infrared radiation from your own body heat spreads outward into the room, carrying energy at that mysterious velocity. Radio waves from distant transmitters pass through the walls around you, their one-way journey times forever uncertain. Even the gentle pressure of the pillow against your head involves electromagnetic forces between atoms, forces that propagate at the speed of light in ways that are simultaneously precise in their effects and ambiguous in their mechanism. Tomorrow, if you wake to sunlight streaming through your window, you'll be seeing our star as it was about 8 minutes ago, or maybe 4 or 16, the uncertainty hidden in plain sight. You'll move through your day coordinating with others, using technologies that assume light speed is isotropic, an assumption that works perfectly even if it might not be true. You'll experience cause and effect, the orderly sequence of events that makes life possible, all mediated by signals that travel at the speed of causality, whether that speed is the same in all directions or varies in ways we cannot detect. This is the quiet miracle of physics, its ability to find solid ground even in the midst of fundamental uncertainty. We cannot measure the one-way speed of light, but we can still build lasers and fiber optic networks. We cannot know if light truly travels the same speed in all directions, but we can still send spacecraft to distant planets with pinpoint accuracy. We cannot step outside of space-time to observe it objectively, but we can still discover its laws and marvel at its structure. The unmeasurable becomes not an obstacle but a feature, a reminder that our knowledge is always embedded within the system we're trying to understand. In the deepest sense, this limitation connects to the nature of consciousness itself. We are patterns of matter and energy that have become aware of ourselves, able to contemplate our own existence and the universe that contains us. But we cannot step outside of our own awareness to observe it from beyond, just as we cannot measure the one-way speed of light without being embedded in the space-time through which it travels. We are part of the mystery we're trying to solve, threads in the tapestry we're trying to see whole. Some philosophers have suggested that this self-referential quality is fundamental to any system complex enough to model itself. Just as Gödel's incompleteness theorem show that mathematical systems cannot prove their own consistency, perhaps physical observers cannot fully measure the framework within which their observations take place. The one-way speed of light might be physics' version of a Gödel sentence, a true statement about nature that cannot be proven within the system of measurements we use to study nature. As sleep draws nearer, as your thoughts perhaps begin to take on that floating quality that comes before dreams, consider one more aspect of this cosmic puzzle. If alien civilizations exist somewhere among the distant stars, they too must grapple with this same limitation. No matter how advanced their technology, no matter how sophisticated their understanding of physics, they cannot measure the one-way speed of light any more than we can. They must choose their own convention, their own way of synchronizing clocks across space. Would they make the same choice we have, assuming isotropy for its simplicity and elegance? Or might they have reasons, perhaps based on the structure of their part of the universe, or the nature of their thought, to choose differently? If we ever make contact with such civilizations, one of our first challenges will be to understand their conventions, to translate between their framework and ours. We would need to find a way to communicate that doesn't depend on assumptions about the one-way speed of light, to build a common language based only on what can be measured round trip. It would be a conversation between beings who share the same physical universe, but might describe it in fundamentally different ways, a meeting of minds across not just space but across conceptual frameworks. The search for a way around this limitation continues in theoretical physics. Some scientists explore modifications to relativity that might make the one-way speed measurable. Others investigate whether quantum entanglement might provide a loophole, a way to synchronize distant clocks without sending signals through space. Still others wonder if the holographic principle, which suggests that all the information in a volume of space can be encoded on its boundary, might offer a new perspective on the question. These are speculative ideas at the frontiers of physics, where established knowledge gives way to creative exploration. But perhaps the most profound lesson of the one-way speed of light is not that we might someday find a way to measure it, but that we've learned to thrive despite being unable to. We've built a civilization that spans the globe and reaches into space, all while navigating around this fundamental uncertainty. We've discovered the laws of nature to extraordinary precision, while acknowledging that some aspects of those laws are conventions rather than discoveries. We've learned to distinguish between what we can know and what we must assume, and to build reliable knowledge on that distinction. This is the mature wisdom of modern physics, its recognition that absolute truth might be less important than consistent, useful description. We don't need to know the one-way speed of light to predict eclipses, design computers, or understand the evolution of stars. We don't need to resolve every philosophical question about the nature of time to build atomic clocks or detect gravitational waves. We can work within our limitations, using them as guides rather than obstacles, letting them shape our understanding without constraining our exploration. As your breathing deepens and your thoughts begin to dissolve into the approaching realm of sleep, you remain connected to this cosmic mystery. Every atom in your body is held together by electromagnetic forces that propagate at light speed. Every thought in your mind involves electrical signals moving through neurons at speeds ultimately limited by light. Every dream you're about to enter will be painted in the colors of remembered light, patterns of electromagnetic radiation that your brain learned to interpret as vision. You are not separate from the mystery of light speed. You are an expression of it, a pattern of matter and energy shaped by the very phenomenon whose one-way journey we cannot measure. The stars continue their ancient burning, pouring light into the cosmic dark at speeds that might be different in different directions, but whose round-trip average remains constant and dependable. Galaxies continue their slow dance, held together by gravity that propagates at the speed of light, or rather at the speed of causality that light happens to achieve. The universe continues its expansion, carrying distant galaxies away from us at speeds that add to the mystery of how their light reaches us across the growing void. And through it all, the one-way speed of light remains unmeasured and unmeasurable, a secret the universe keeps even as it reveals so many others, in this quiet moment, suspended between waking and sleep, between known and unknown, you can feel how science is not about having all the answers, but about engaging with the questions in productive ways. The mystery of light's one-way speed doesn't diminish our understanding. It enriches it, adding depth and subtlety to our picture of reality. It reminds us that the universe is not a puzzle to be solved completely, but a mystery to be explored endlessly, each answer revealing new questions, each measurement defining new limits to measurement. Perhaps this is why the question of light speed continues to fascinate physicists and philosophers more than a century after Einstein showed it was unanswerable. It's not just about light or speed or measurement, it's about the nature of knowledge itself, the relationship between observer and observed, the role of convention in our descriptions of nature. It touches on the deepest questions we can ask about reality. What can be known? What must be assumed? How does the structure of space-time constrain the beings within it who seek to understand that structure? These are not questions that keep us awake with anxiety, but rather thoughts that can guide us gently towards sleep, reminders of our place in a universe far grander and more mysterious than our daily concerns. The unmeasurable one-way speed of light is like a Zen koan for physics, a paradox that doesn't demand resolution but rather invites contemplation. It teaches us humility in the face of nature's subtlety, and shows us that even our most precise sciences rest on foundations that include elements of choice and convention, alongside discovery and measurement. Tomorrow the sun will rise, its light reaching you at whatever one-way speed the universe actually employs, masked forever behind the round-trip average we can measure. You'll go about your day never knowing whether the light from objects around you arrives instantly or with delay, the universe's perfect compensation hiding any asymmetry from your perception. And that's perfectly fine. The unmeasurable remains unmeasurable, but life continues, science advances, and our understanding deepens even within the constraints of what we cannot know. As you drift now towards sleep, carried by the slow tide of exhaustion into the realm of dreams, you take with you this gentle mystery. Somewhere in the quantum foam at the smallest scales of reality, virtual photons flicker in and out of existence, carrying forces at the speed of light. Somewhere in the vast cosmic web, light from the first stars still travels through space, its one-way speed a secret it will never reveal. And here, in this quiet moment, you rest at the intersection of all these mysteries, a conscious being in a universe that keeps some of its deepest truths forever hidden, not as a cruel joke, but as a fundamental feature of its architecture. The question that seemed simple at the beginning of our journey together, why has no one measured the speed of light, has revealed itself to be a doorway into the deepest mysteries of physics and philosophy. It has shown us that even our most basic measurements rest on assumptions we cannot verify, that our most precise sciences include elements of convention alongside discovery. It has taught us that limitations in knowledge are not failures, but features, aspects of how consciousness embedded in space-time must necessarily experience and describe that space-time. And now, as sleep approaches with its own mysteries and unmeasurable experiences, you can release the need to measure and know everything. You can rest in the understanding that some questions are more valuable for the wondering they inspire than for any answer they might have. The one-way speed of light will remain unmeasured when you wake, just as it was when you began listening to these words. But perhaps your understanding of what that means, of how mystery and knowledge interweave in the fabric of physics, has shifted like light itself, moving through the space of thought at speeds we can contemplate but never quite capture. In the end, the universe keeps its secret not because it's hiding something from us, but because the secret and the seeking are part of the same phenomenon. We cannot measure the one-way speed of light because we are within the system that light speed helps define. We are made of star stuff, as Carl Sagan said, but more than that, we are made of light stuff, patterns of electromagnetic energy that have become complex enough to wonder about our own nature. The mystery is not outside us waiting to be solved, but woven into our very being, part of what makes consciousness and cosmos a single, unified, quietly wonderful whole. And as you drift into sleep, you remain part of this quiet universe, wrapped in its laws, carried by its mysteries, gently, peacefully, into the night where dreams themselves travel at speeds unknown and unknowable, where time stretches and compresses according to its own dream logic, where the questions of physics give way to the deeper rhythms of rest and restoration. The speed of light, measured or unmeasured, continues its constant dance through space and time, and you, dear listener, are part of that dance even in sleep, even in dreams, even in the quiet spaces between thoughts, where the universe whispers its secrets in languages we're only beginning to learn to hear.